So a big question that we want to answer is how to evaluate. Double integrals. And the idea here is actually very clever. It's using what's called iterated integration. The main idea being that the double integral over region R, and we'll stick with a very simple region R for the first couple examples, because it turns out that the more general of a region R that we use, the more careful we have to be when determining the bounds of integration for a region. So we'll start with how to evaluate the double integral over rectangular domains. So we denote a rectangular domain in a similar interval notation to how we denote an interval in 1D. We say that a rectangular domain, say, from A to B in 2D consists of two intervals. The first interval is an interval along the x-axis, going from the minimum value of the domain to the maximum value of the domain, or from, say, A to B, and then from C to D along the y-axis. So this rectangle R is the simplest possible shape that we can integrate over. So this is what we'll start with in terms of evaluating an integral. The idea is that the double integral of a function can also be written as the double integral from A to B in x, from C to D in y of that function. Notationally speaking, we can say then that dA is the same thing as dy dx. So this is the notation that we use for integration over rectangular intervals, where x goes from A to B and y goes from C to D. Now, it's very important to remember the order here. If you don't order the bounds correctly, then you might calculate the wrong value. The outer bounds of integration always have to be with this outer variable. So this dx here is connected in some sense to these bounds, A to B, and this dy here is connected to these bounds right here from C to D. You don't always write the following, but it's a good idea to maybe get in the habit to do this the first couple examples that you do of a double integral, because this notation right here really means something very specific. It means calculate an iterated integral. So you calculate the integral from A to B of the integral from C to D of the function with respect to y. And then the result that you get from this integration, you do the integral of the function from A to B. So we don't always write these boxes here, but it's nice to write this at least a couple times. Whenever you see this iterated integration, the innermost bound of integration is connected with the innermost variable here. This is called the inner integral, or the inner iterated integral. And then the outer integral, or the outermost iterated integral, is this x integral. It's the outer integral. So the idea is that when you're determining the bounds, you want to start from the outside and move in And then when you evaluate the integral, you want to do the innermost integral first and move out. That's kind of like a reverse procedure. Determining the bounds, you start with the outer integral and move in, and then when you evaluate the integral, you have to do the inner integral first and then move out. And this may not seem too important for rectangular domains, and it turns out it's not when we talk about what's called Fubini's theorem. Right? Fubini's theorem will tell us that we can do a given rectangular integral in any order that we want. However, we have to be a little bit more careful when we're talking about more complicated domains. We can still choose any order that we want, but determining the bounds for a non-rectangular domain is often very difficult. So we'll see how to do this correctly when we get to Fubini's theorem. But let's go through and do a couple examples of an iterated integral over a rectangular domain, just to kind of get that nailed down and get it specific for a couple different examples. We know how to do this. So we take the double integral from 1 to 2 and 3 to 4 of the function x squared plus y squared plus 2xy dy dx. Now this is the same thing as the double integral over the region R of the function x squared plus y squared plus 2xy. And really, if you want to draw a picture of this, we're taking the accumulation of this function over the rectangular domain for x from 1 to 2, and then y from 3 to 4. So the value that we get here, this is our region R, and the value that we get when we evaluate this is the total accumulation of this function inside this rectangle. So we go through and do this. We do the inner integral first. The inner integral is the integral with respect to y of this function. So we integrate this function with respect to y, and we know that from calculus 2 that the simplest way of doing that is finding the antiderivative of this function, and it's with respect to y. So the inner integral, it's similar to doing the partial derivative. When we're doing the inner integral with respect to y, and we're searching for the antiderivative of this function with respect to y, we treat x as constant and proceed to take the antiderivative. So if x squared is constant with respect to y, so the antiderivative of it is going to be x squared times y. Antiderivative of y squared is going to be y cubed over 3 from the power rule. And the antiderivative of 2xy is going to be 2x times y squared over 2. And then from the fundamental theorem of calculus, we have to evaluate this at our y bounds. And when we do this, we get 4 times x squared plus 4 cubed over 3 plus x times 4 squared minus 3x squared plus 3 cubed over 3 plus 3 cubed times x. which simplifies to the following. It'll be x squared plus 7x plus 37 over 3. When you go through and simplify this expression right here. So once you do that, once you do this simplification, this is what you get. The double integral reduces. So we've done our first integration right here. It reduces to the single variable integral of this function from 1 to 2, which we can evaluate by, again, going through and finding the antiderivative of this expression, which is x cubed over 3 plus 7x over 2, x squared over 2, plus 37 over 3 times x. And when we plug in our bounds here from 2 to 1, this becomes 2 cubed over 3 plus 7 times 2 squared over 2 plus 37 over 3 times 2 minus the lower bound plugged into this function, which is 1 cubed over 3 plus 7 times 1 squared over 2 plus 37 over 3. And so this simplifies when you go through and do the arithmetic here and simplify everything down. This number just simplifies to 151 over 6, which is the exact value of this double integral. This is approximately equal to 25.16. So there you have it. This is the exact value of this double integral. So it's the accumulation over this rectangular region R of this function. And because the function is positive, this is actually equivalent to the volume under the region, under this function, over this region, over this rectangular region. So this is a very, very powerful idea. So just to kind of confirm what we've been doing so far, what we're seeing right now is the Riemann sum approximation converging to the actual value, which we found to be 151 divided by 6, or approximately equal to 25.16. And this is showing that this computational procedure that we've developed for evaluating iterated integrals on rectangular domains is giving us the actual correct result, which is awesome. And we'll see in a couple more examples this done out, so that we really kind of get a hold for how to integrate over rectangular domains in 3D. And in subsequent lectures, we'll see how to integrate over more complicated domains, and we'll use varying different methods to do so. We'll do one more example to kind of show that we can directly go through and use these iterated integrals in a very nice fashion. So let's just consider the double integral for x from 0 to 1, y from 0 to 1 of the function x times cosine of xy. So the inner iterated integral here is the iterated integral from 0 to 1 of this function with respect to y. This is our inner iterated integral. And we can go through and evaluate this right away. The x is constant with respect to y, so this comes out of this integral. And we're just left with the antiderivative of the function cosine of xy, which is going to be given by the function 1 over x times sine of x times y. This is the antiderivative of the function cosine of xy with respect to y. Because if you take the derivative of this expression with respect to y, you're going to get this cosine of x times y here. So we have to evaluate this from 1 to 0. The x times 1 over x becomes 1, so that cancels out. And when we plug in our y bounds here, this is going to become sine of x times 1 minus sine of x times 0, which is sine of 0, or 0. This is just equal to the integral from 0 to 1 of sine of x dx, which is the antiderivative, or negative cosine of x, of this function, evaluated at the upper x bound and the lower x bound, which is going to be negative cosine of 1 minus negative cosine of 0, or 1 minus cosine of 1. And this value is exactly the correct value of the double integral of the function x times cosine of xy over this region R. That's the accumulation of this function over this region. So this is the method of doing iterated integrals over a rectangular domain, and it's our starting point for how we're going to be going through and thinking about evaluating the double integral of these functions over many different types of domains. And so here we're seeing, again, just a visualization that we're integrating the double integral of the function from 0 to 1 in x, 0 to 1 in y. We've obtained that the exact value is 1 minus cosine of 1, which is approximately 0.45969. And sure enough, as we increase the number of rectangles in our Riemann sum, we're getting closer and closer and closer to that exact value. So this is very cool and neat, I think, to see this displayed out. And in the next few lectures, we'll get into how to implement this integration, double integration, on more complicated domains, and some very useful techniques that we have of doing that. So I think we'll consider one more example just to kind of bring this home and kind of show that we can use this procedure to get many different types of geometric formulas that are analogous to formulas that we might obtain in a 2D setting for 2D geometric properties. And what I'll ask you to remember is that if we have, say, any trapezoidal figure, say, for instance, you have a trapezoidal figure that looks like this in 2D. The area of this trapezoidal figure is given by the width of the base the size of the base multiplied by the average height. So the height of at the midpoint right here of this trapezoid is, we'll call it h. It's this width of this trapezoidal figure times the average height between the lowest point in the trapezoid and the highest point in the trapezoid. So it turns out that we actually have a very similar formula for, in 3D for the volume of a trapezoidal shape with a rectangular base, or with a square base. And we can prove this directly, figure out what this formula is directly using the double integral. So suppose that we have some rectangular base here to our trapezoid. It's a trapezoidal prism, say, we could think of it as. And specifically, let's say that along the y-axis, this base goes from C to D on the y-axis, and it goes from A to B on the x-axis. So it's a rectangular base, the top of which is given by a plane. Any trapezoidal prism has a top, which is going to be given by some plane. So the top of this trapezoid is a plane, therefore it's going to have the equation z is equal to mx plus ny plus L. And we're going to assume that the values m, n, and L are giving us a plane that is above the xy plane. So you have a picture that looks like this. Even if you don't, you still have the net volume under that plane, but we just want to get a general formula that's similar to the equation in 2D, for a trapezoid in 2D, but for the volume of this plane. So if z is positive, then the volume under this plane, for the volume under z equals mx plus ny plus L, is exactly equal to the double integral over this region. So it's the double integral over the region R of mx plus ny plus L dA, or in terms of our exact bounds, it's the double integral as x goes from A to B, as y goes from C to D, of mx plus ny plus L dy dx. This becomes the double integral, the integral from A to B, from C to D. And we can directly go through and do this first iterated integral. It's the antiderivative of this function with respect to y, which is going to be mx times y plus ny squared over 2 plus L times y, evaluated from D to C. And then we still have to take the outer integral of this function. But let's simplify it a little bit first. So when we plug in our bounds, C and D, we get the integral from A to B of, this will be mx times D minus C plus n over 2 d squared minus c squared plus L times d minus c. This is what we get when we plug into that fundamental theorem of calculus. We plug in our upper bound and we subtract this function plugged in with our lower bound. And we can even do some cleaning up here and some more simplification. So before we do this integral, remember that d squared minus c squared is the same thing as d plus c times d minus c. So we can factor out d minus c from every term on this expression. So this integral will be the same thing as d minus c times the integral from a to b of mx plus n over 2 times d plus c plus L. It's always nice when you can sort of simplify things as much as possible. So when we go through and do the antiderivative of this expression, we get that this is going to be mx squared over 2 plus n over 2 times d plus c times x plus L times x. Because the integral of mx is mx squared over 2. The integral or antiderivative of n over 2 times d plus c is constant, so it's going to be n over 2 times d plus c times x. And same thing with L here, the antiderivative of that is going to be L times x. This will be equal to d minus c. When you plug in the bounds for x, you have m over 2 times b squared minus a squared plus n over 2 times d plus c times b minus a plus L times b minus a. And notice again that we have another thing. We have this b squared minus a squared, which is the same thing as b plus a times b minus a. So I can factor out a b minus a from every single one of these terms in this expression, which gives me d minus c times b minus a times m over 2 b plus a plus n over 2 d plus c plus L. And this value is the value of the volume. The volume under Z is mx plus ny plus L over this rectangular region R. This is equal to d minus c times b minus a times m b plus a over 2 plus n c plus d over 2 plus L. And what this formula is telling us is a direct analog of the previous formula from 2D for a parallelogram, because it's telling us that this d minus c times b minus a is the area of the rectangular base multiplied by the height of this trapezoidal pyramid at the midpoint. Okay, this value in parentheses right here is the height of this triangular pyramid at the midpoint, because b plus a over 2 is the midpoint, the average value of this base in the x, along x, and this is the average value along y, or along the y-axis. So this value, this height at the midpoint, is exactly the height at this point right here, at the midpoint of the parallelogram, or the height at this point right here. So if this right here, this height right here is h, and then a is the area of the base, we're seeing that the volume of this trapezoidal pyramid is going to be this area of the base times this height right here, which is a direct generalization of our previous formula using the double integral. And so here I've plotted out the graph of the function for m equals 3, n equals 2, and L equals 1. And we're very clearly seeing that the Riemann sum is very quickly converging to the correct value, which for those values m of m, n, and L, the correct volume is 6. And very, very quickly you see the Riemann sum is getting closer and closer and closer to the actual value of the volume under this plane, which is verifying the result that we just obtained. So this is a very neat example for many reasons, but mainly because it's showing that we can use this idea to derive general formulas for volume in general in 3D using double integration. I think this is a very cool example to end the lecture with, because it shows us that we can actually derive very general formulas for geometric shapes using the double integral. And we'll see how to expand this in the next lecture when we consider some properties and more detailed examples that use non-rectangular domains. And that will be essentially explained in the lecture after that when we talk about Fubini's theorem. But thank you very much for coming to lecture today. I hope you all learned something and had a great day.